Hello, this is Ms. Nichols, and this is the second lecture in our magnetism unit. The topic is magnetic fields. The essential question is, how do we determine the size and the direction of a magnetic field? Magnetic field is going to be a new variable for us. We're going to use capital B to represent magnetic field strength in an equation. And all magnets make magnetic fields. So whether we're talking about a permanent magnet or a current-carrying wire or just a free-floating charged particle, they are going to exude this magnetic field in the space around them. So here's a few just like pictures of magnetic fields around a variety of different kinds of magnets, plain current going through a wire, loops of wire, a solenoid, which is lots of loops of wire, a bar magnet, which maybe you've seen before, and the Earth itself is a magnet. So all of these magnets are caused by moving charged particles at some level, and they spread their magnetic field around them in the space all the way to infinity. Magnetic fields are going to be vectors, which means that they are having magnitude, which is sometimes known as strength or size, and also a direction. If you remember the other fields we've covered in our class, the electric field and the gravitational field, you'll remember that in general, force fields are defined as the amount of force per some sort of fundamental thing, right? So gravitational field, G, is the force per kilogram of mass. Electric field is the force per coulomb of charge. The magnetic field is the force per coulomb meter every second, because to make a magnet, you have to have charge and velocity. So the units of B are the Newton per coulomb meter per second. Of course, nobody wants to write that, so we have shortened that to something called a Tesla, or capital T. So the units of B are T. When we're drawing a magnetic field, if we want to show a strong magnetic field, we'll make those field lines either very dense or very bold or very long, just like when we draw other kinds of fields in other diagrams. We also need to indicate something about the direction of the magnetic field. Remember that we sort of have conventions for those things. For gravitational, we always point in the direction the mass would feel force. For electric fields, the field arrows point in the direction of force on a positive charge. And for magnetic fields, the arrows are going to point in the direction that a north pole of a test magnet or a compass would feel. So if you put a compass in a magnetic field, whichever way the north arrow is pointing, that is the direction we're going to draw the arrowheads in that field. Of course, the south pole feels a force in the opposite direction. One more note that you may see in these drawings is that magnetic fields are all closed loops. That means that every magnetic field line that you draw has to connect back to itself somewhere. It's easy to see in that current in the wire, right? You can see those magnetic field lines connecting to themselves, and even in that loop of wire. In the solenoid, right, they kind of curl out, but then they connect back to themselves up through the middle of the solenoid. And actually the same thing is happening in the bar magnet. They're coming out one end and they are connecting back to themselves through the bar magnet. And the same thing is true through Earth. So magnetic fields are always going to be closed loops. Here's kind of an interesting fun fact about Earth's magnet. So we know that Earth has a magnetic field, and we've used that to navigate because we know that when we put a compass anywhere on the surface of Earth, the north pole of the compass points north. But of course, the way we've defined magnetic fields is that north compass attracts to south of another magnet, which means that the north geographic pole of Earth is actually the south pole of Earth's compass, of Earth's magnet, because it's attracting the north pole of our compasses. So everything you ever heard about the North Pole is a lie. Earth's north pole is actually in the south and vice versa. The typical magnets that you see and may have played with before are known as dipoles. A dipole is a magnet that has a north and a south pole, a single north and a single south pole. And that's the typical bar magnet, for example. When you are trying to draw a field pattern or a vector map for the magnetic field of a dipole, as you probably saw in those last slides, the magnetic field lines are all going to leave the North Pole and then go back in the magnet on the South Pole and then continue and connect up with themselves. This is a very similar pattern that you would see with a distribution of charges that contains a single positive and a single negative charge. It creates the same magnetic field pattern as the electric field when you have opposite charges in a space. So for magnetism, this is known as a dipole. When you look at that diagram, you'll notice that the field lines are densest sort of close to the poles and close to the magnet. That means that's where the magnetic field is strongest, and as you move away, the magnetic field gets weaker. The math to calculate by what fraction the field changes strength is actually really complicated for a bar magnet, so we don't have any equations for dipoles in this class. It decreases by a factor of r squared when it's close and r cubed when it's further away, so it's a really pretty complicated mathematical series of equations. So you just need to know the general gist of the fact that fields are strong close to the permanent magnets and they get weaker as you move farther away. Earth, of course, can be modeled as an ideal bar magnet, which is basically the same as that bar net magnet, but rotated 90 degrees. And as we mentioned, the south pole of Earth is actually in the north and vice versa. So the field lines from Earth look very similar to the field lines for that bar magnet dipole. Turns out, though, Earth is actually way more complicated than that, because Earth's magnetic field is actually caused by the movement of molten iron in the Earth's outer core and mantle. And because there's convection currents and all sorts of weirdness, Earth actually has lots of little localized north and south poles, all different places around the globe. So when we actually map Earth's magnetic field, it's really crazy and complicated. And if you go into deeper physics or geophysics, you'll learn about that. The other dipole magnet that I want to bring up is known as a horseshoe magnet. So a horseshoe magnet is essentially if you take that bar magnet and you bend it in the shape of a horseshoe so that the two ends are close to each other. You've probably seen these things before, right? And so you can imagine taking those magnetic field lines and sort of just bending them so that they are in a U shape. What that actually does is something really useful in physics. It creates a region right there in the middle of that horseshoe magnet where the field lines are parallel to each other and relatively equidistant, equal spacing. That tells me that the strength and the direction of the field in that area is relatively uniform. Of course, physicists and engineers love uniform fields because objects in those fields behave predictably. The amount of force doesn't change no matter where they are, and this is why horseshoe magnets are actually really heavily used in industry. Unlike bar magnets, because wherever you move in that bar magnet, your field is changing in strength as you get closer or further away. So uniform magnetic field is created in the center of horseshoe magnets. If you hear a uniform magnetic field in a problem, that must be the way we're creating it by and large. So while the magnetic field created by permanent magnets is complicated, it turns out it's simpler to describe magnetic field from wires. So we do have an equation that lets us calculate the magnetic field strength from a current carrying wire. As we described earlier, anytime you have wire with a current flowing through it, we are going to create magnetic fields in the space around that wire. When you actually do this experiment, so this is like a wire running through the paper with a bunch of like iron filings or something sprinkled on the paper, you can see the shape of those field lines is actually circular around the wire. And you can also see that there are some places in that diagram where the field is stronger because it's pushing and pulling more of those iron filings, and there's other places where they're not quite as impacted. So what does the strength of the magnetic field created by a wire depend on? Well, it depends on two things, actually. It depends on the current. So obviously, the more current you flow through the wire, the stronger the wire magnet is going to be. That should be intuitive since magnetism is caused by moving charges. And it's actually a linear relationship between B and I. The other thing it depends on is the distance. So you should be able to see that the magnetic field is stronger when we are closer to the wire. B is actually inversely related to R. It's a plane inverse. It's not an inverse square, which is a little different than our other fields that we were dealing with. And that's just because it's a complex situation involving charges flowing through the wire. So the charges, it's like all of the individual electrons that we have to add up the contributions of all of those. The equation for B for a current carrying wire, so this is a very specific, this equation only works for a current carrying wire, is B equals mu naught over 2 pi times I over R. So you see that linear relationship with I on the top, and we see the inverse relationship with R on the bottom. Mu naught is a constant, we've seen it before. It is called the vacuum permeability, and it's equal to 4 pi times 10 to the negative 7th if you actually have to do this calculation. And of course, 2 pi is a constant as well. So those pi's cancel out. You just end up basically with 2 times 10 to the negative 7th once you do 4 pi divided by 2 pi. So in any case, that is the equation to calculate the strength of the magnetic field around a current carrying wire. You often will get questions that say, so if we double the distance, what happens to the magnetic field? And in this case, it would have, because it's inversely related. So that equation on the last slide let us calculate the magnitude of magnetic field. And as you'll discover in this unit, finding the magnitude of things in this unit is actually the easy part. The challenging thing in magnetism is figuring out the direction that things are going to act. And the reason is because magnetism is really weird. We are used to fields and forces acting parallel to each other. In other words, gravitation field is up and down, and when you drop an object, it falls down. Same thing with electric field strength. Whichever way the field strength is pointing, or the field is pointing, that's the direction of the force. Magnetism, it actually is not in the same direction as the field. In fact, magnetic interactions always occur in 3 dimensions, which means we can't even draw these things flat on the surface of paper. And we'll talk a little bit about why in class. But for now, you need to have a tool to draw things in 3 dimensions. Specifically, we need to be able to draw vectors in 3 dimensions. So we're going to assume that our paper is our reference frame for this, which means that according to the paper, okay, the x-axis is essentially going to be called left and right. So if you hear a magnetic field pointing to the left, you're going to draw an arrow pointing to the left and label it B. If you hear current to the right, you're going to draw an arrow to the right and label it I. So x-axis is going to be called left and right. The y-axis we're going to refer to as up and down. And so that's a little bit weird because it's not like up this way, it's like up towards the computer. But that's how you would draw an up arrow on your paper, so it works pretty well as well. So up, if something is going up, you're going to draw an arrow to the top of your paper, and down is down. So the last axis we have to describe is the z-axis. So the z-axis is the axis coming in and out of your paper. So we're going to describe out as something popping up towards the ceiling, and in as something driving in towards the floor. How do we draw arrows coming in and out of our paper? Well, you actually, if you've ever seen a real arrow, you can imagine a real arrow going in and out of the paper and what you would look like. Arrows have like a point on one end and they have like a little feather on the other end. So if you had shot an arrow straight down into your paper, you would see the feather or the X kind of on the back of that arrow. And so when we draw vectors going into our paper, you will see them represented with X's or sometimes X's with a circle around them. That represents in. So if you have a magnetic field in, you'll draw a bunch of X's. Out, if you imagine the arrow coming out of the paper, it would be like the tip of the arrow coming out at you. And so we're going to draw out vectors with either just a plain dot or a dot with a circle around it. And this can be any of our vectors, field, force, current, any of those kinds of things, velocity, can be represented with any of these vector arrows. So now that we know how to draw arrows in 3 dimensions, how do we actually determine the magnetic field direction from a current carrying wire? We're going to use something known as the first right-hand rule. There's 2 right-hand rules in magnetism. The first one specifically determines the direction of magnetic field around current carrying wires. In order to do the right-hand rule, you need a very handy-dandy tool, your right hand. Okay, I know it looks left on the screen because I'm backwards, but anyway, this is my right hand, and that's what you're going to be using for the right-hand rule. So if you're a righty, you have to put down your pencil in order to do the right-hand rule, so make sure you keep that in mind. So the first right-hand rule, the way it works is, you're going to take your right thumb and you're going to point it in the direction of the current in the wire. Okay, so the right thumb points in the direction of the current in the wire, just like shown in that diagram. Then then you are going to curl your fingers around the wire. So imagine yourself grabbing the wire, and the tips of your fingers are going to point in the direction of the field at a certain location. So you can see in that drawing how that magnetic field is kind of curling around the wire in a very specific direction. If you wanted to draw this out symbolically, I would draw my wire sideways, and then I would actually put in and out arrows above and below the wire. So my fingers are coming out above that wire, so I've drawn out arrowheads on top of the wire to represent the magnetic field, and then your fingers would plunge back into your paper on the bottom side of the wire, and so I've drawn in magnetic field arrows to represent that the field goes in that location, and an eye going to the right. A note that the magnetic field weakens with distance. Remember, it's that inverse relationship, so I've drawn more of those arrows close to the wire to show that that's stronger, and fewer of those arrows as we move out. It would technically extend into infinity, but I only drew a small portion of that diagram. Here's another example for you. Okay, so this time the wire is actually going in and out of the page, so it's hard to see. You're just seeing kind of a cross section of the wire, but it's labeled I with an X that shows that current is going in. So grab your right hand, point your thumb into your paper, so straight down to the floor, and you will see that your fingers curl around that wire in the direction that those arrows are pointing in that diagram. So you would draw your magnetic field as closed loops surrounding that wire. And just a reminder, what that means, you got to put arrowheads on your magnetic field lines. Those arrowheads mean that if I stuck some compasses at different locations, the needles would be deflected in the same direction as the arrow. So it shows this diagram. I like it because it shows 4 pictures of compasses. What would the compass actually do if you stuck it at those locations near the current carrying wire? All right, we've reached the end of the video. So the essential question is, how do we determine the size and direction of a magnetic field? Depends whether we're talking about permanent magnets or current carrying wires. So hopefully you understand how to do it in both of those cases. And we will do a bunch of practice with this in class. Thanks for watching.